Hey class, so number 68 is a pretty fun and tricky problem here, so I thought I would make a video for you guys to talk about it a little bit. So, let's discuss what we got going on in here. We have a block 1 here that starts at a position when it's up at the top. Alright, so if we call this setup that we see here, maybe setup A, then at some time later on we have a situation which maybe we'll call situation B, where we now have a beautiful art. Alright, we now have block 1 that's moving here, and it's just about to collide with block number 2, which is right here. Alright, so that's situation B. Then going along with the same idea, we'll have another situation a little bit later. My picture's getting more and more beautiful by the moment, where now we're going to have a situation that's right after the collision, and so one or both of these will be moving forward, depending on whether we're in part A or B. They might be moving together or they might not, but we're going to go ahead and call that situation C. And then lastly, I'll move up just a little bit more here, we'll have another situation in time which we'll call situation D, and that's when the two objects have moved out and are now at rest. So now they've moved maybe together, maybe not, depending on the situation, but we know that they're at rest. Okay? So those are our three situations. Interesting. I wonder what or how we can even look at breaking this down. Alright, so the reason that I did this is to consider what we have going on in each of the different situations. Alright, so if we consider from A to B, all we really have is block 1 moving. Block 2 stays stationary the entire time, and block A is moving, or block 1 is moving from some height down to the ground on a frictionless curve. So that makes me think of using conservation of energy for block 1. Okay, because we know that it starts at some height, so we have mgh, its potential energy that it starts with, and that's going to be equal to what it has when it's down below, which is just kinetic energy, 1/2 mv squared. And so straight away we can determine what the velocity is of block 1 in picture B, at that point in time, by looking at conservation of energy. Our masses will cancel out, and we can find that the velocity of block 1 in picture B, or at point B, is just going to be equal to the square root of 2gh. Cool, that's fun. Now what about looking at B to C? So this is why I broke things up to look at just before and just after my collision, because now I can look at conservation of momentum. Alright, and so we can look at conservation of momentum. Now in part A of the question, it's an elastic collision. In part B, it's an inelastic collision. So we're going to come back to that in a minute, because I want to, basically, and because there's some variation. But what I want to do is look at from C to D, because what we're really trying to determine is the distance that everything moves, right? We're trying to find the distance from where it started. So if this is where it started here, then we want to find this distance, how far it slides along here, right? And so looking at that transition, maybe I'll give myself just a little more room down here. If we're looking at the situation from going from point C to point D, it makes me think of, once again, conservation of energy. And so now what we have is we start with kinetic energy, 1/2 mv, maybe we'll call it vc, the velocity at point C, squared, minus work done, or plus work done by outside forces, which the work done here is going to be work done by friction, which we know to be negative, so minus the force of kinetic friction times the distance, and then that equals the energy we end up with. It stops on level flat ground, so we're going to have 0 final energy. So here's the D we want to find, if we can find what mass is moving and what its speed is at point C, then we can determine that distance d. Alright, so the key then becomes determining how fast block 2 is moving at point C, because we're trying to find the distance that it goes. Alright, so now this is where we have two different variations. We can look at part A, where we have an elastic collision, and so if we have an elastic collision, that means that the velocity at point C after the collision of block 2, so the velocity of block 2 at point C is going to be equal to, based on the equations we learned in class just the other day, 2m1 divided by m1 plus m2, and then multiplied by the initial velocity of block 1. Well, the initial velocity is the velocity just before the collision, and that is our v1b. So there we go, we can get v2 of block C, and so then block C would be sliding out to point D here, which we would find later. Cool. And then in part B, we have a different situation. We have an inelastic collision. So for the inelastic collision, now we're going to have conservation of momentum, where we have mass 1 multiplied by its initial velocity, which is v1b, the same value here, is now going to be equal to the momentum after the collision. And so after the collision, the two masses are sticking together because we're told it's an inelastic collision. So we're going to have m1 plus m2, and multiplied by then just their combined mass, which I'll just call Vc, since the two of them are moving together at that speed. And so here you can find the Vc, here it's just V2c, but both of those are what you should be able to use down here in your conservation of energy equation to find your distance d. Alright, so I know that's not solving everything for you, but hopefully that gets you started. Let me know if you have any questions as you move forward with this fun and challenging problem. God bless.